Okay, so welcome everyone to week 7 of the earthquake and masonry structure design. So in this week, we will be looking at the design of masonry structure, unreinforced masonry structure under compression. And the objective of this week is to design member in compression or under compression using the simple and refined methods, using the Australian standard 3700 for masonry structures. Okay, other tasks you will need to do for the course, you will need to attend the lecture or which is a online recording and then go through the lecture slide. Then other tasks related to the earthquake part. So you need to continue working on the project and you can start model the building on space gas to complete the dynamic analysis part of this assignment. Okay, and now let's start looking at the slides. Do you all can see the slides? Everything is okay?
Yes.
Okay. Just confirm with me if there is any problem or any issue, just let me know, please. Thank you. So let's start our lecture. So this week we are looking at masonry structures under or subject to compression loads. So we were looking firstly in this lecture to the unreinforced masonry walls or unreinforced masonry structure, which we can call it URM. So URM is the unreinforced masonry. This will be our topic today, and we are looking at the compression, under compression. We have two methods of design for unreinforced masonry under compression. The two methods are design using simple rules, which is covered under clause 7.3.3, and design by refined calculation, which is covered by clause 7.3.4. The simple rules is simplified method and a little bit conservative, but the refined method is, as you expect, it is a complicated method, but less conservative. So each one has some advantage and some disadvantage. So based on the case you have in your design, you can select which method to follow or to use. Both of them are available or are covered in the Standard 3700 2018 version. So for the design of members under compression, we have general rules or general uh, hints in clause 7.2. These hints are given by the standard are the wall or the unreinforced masonry wall should be designed for compression only if the vertical compressive stress less than 3 point F dash or F prime MT. So because the walls or the masonry walls are sometimes under compression and bending. So if they are under compression and bending, we can only design the compression so that we can ignore the bending in these cases. So we can ignore the bending in these cases if the compressive stress applied to the wall is less than 3 F prime MT and the bending moments are small enough to be ignored. Okay, so FMT prime is given by the standard as 0.2 MBA, which is the characteristic flexure tensile strength of the masonry. Okay, so this means that we can ignore the bending moments if the compressive or vertical compressive strength less than 0.6 MBA. And this also means that simultaneous effects or combination of vertical and horizontal loads are not required in this case. Okay, so this is some instruction given by the standard, so we can use this instruction. So for walls under compression, we will look at the failure mode and what to consider in our design. So for design purposes, minimum eccentricity should be considered, and the possible failure modes are. So because we just design for compression only, we should consider E minimum or minimum eccentricity, because in most cases the load will not be applied to the centroid or the center line of the wall, so that we should consider minimum eccentricity. And the failure modes of the wall in this case shall be one of two. The first one is the wall can fail under compression, or the masonry can fail under compression on the inside face of the member. So if we have a wall, the inside face of the wall will or might fail under compression. The other possible failure mode is buckling failure mode, with total collapse occurring when the tensile strength is exceeded on outside face of the member. So this means that we can have two types of failure. One of them is local failure, and one of them is global or overall failure of the wall. So the first, or the local failure, the compression failure occur at the or on the inner face of the member. For the global or overall failure, it happened due to buckling, with total collapse of the member occurring when the failure in case 2, when the tensile strength more than the allowable tensile strength of the wall, which we have used in the previous slide, F MT prime. Okay, so these are the two possible failure modes we can have in our design of wall under compression. The compressive capacity of the member, or when we are designing a masonry wall under compression, we should consider the following parameters. The first parameter is the slenderness ratio of the wall, SRS or SR. SRS means simplified slenderness ratio, and SR is the slenderness ratio. So because we have two methods, as you know from the previous slides, so we can have SR or SR. We will SRS for simplified method, SR for the refined method. We will know how to calculate both of them later. Number two is the effective eccentricity of the compressive loading at each end of the wall, E. So in some cases, when we have a wall like that, so the load may not be applied to the center of the wall. If this is the center line of the wall, so we may have different eccentricity at the top and at the bottom. For example, something like this. So we should know what is the eccentricity E at the top, what is the eccentricity E at the bottom. The third parameter we should consider is the compressive strength of the masonry, which is Fm prime, compressive strength of the masonry. Number four is the cross-section area of the member or the masonry. We have two, AB and AC. AB is the bedding area, and AC is the compression area. Okay, so these are two cross-section area we need when we are considering or we are designing the member under compression. Do you have any query, guys, up to here? No? Okay. Thank you, Brendan. So these are the parameters or the factors that are considered when we are designing or we are finding the compressive capacity of a masonry member. And in this slide, this is some of the how to find the parameters. Okay, so let's have a look here. We mentioned earlier FM. FM is the compressive strength of masonry. So compressive strength of masonry can be found or can be determined using this formula. Fm prime equal to Kh multiplied by Fm prime. So to find the characteristic strength of compressive of the wall, Fm prime, we need two parameters, Kh and Fmb. Fmb can be found using table 3.1 here. Kh will be found using table 3.2. So based on the type of masonry unit, if it is clay or concrete or calcium silicate, and the bedding type between the bricks or between the masonry units, we have full or face shell, and also the mortar class M2 or M3 or M4. We will see this in the examples. And based on the characteristic unconfined compressive strength between 5 to 50, you can find the value of FMB prime. So the values here are the values of FMB prime based on FUC prime, mortar class, bedding type, and type of the masonry. So this is the first parameter. Second parameter, which is KH. KH is the joint thickness factor. Come from table 3.2. Based on what? Based on or according to the ratio of masonry unit height to mortar bed joint thickness. So it is a ratio between the height of the unit. Let's assume this is the height of the unit which is HU, to the thickness of the joint. So if we have a joint or bedding between the two bricks or the two units, so the thickness of the joint is TJ. So this is the joint. Okay, so this ratio is HU over TG. So based on this ratio, you can come to the table to find the factor KH. Another option to find KH using this formula. So KH is the joint thickness factor equal to 1.3 HU divided by 19 TJ to the power 0.29, where HU is the block height, TJ is the joint thickness. Okay, a condition here by the standard that KH should be less than or equal to 1.3. So the maximum KH is 1.3, and you can find this in this table. So this is the maximum value for KH. Okay. This formula we used for Fm prime is just for clay and concrete and calcium silicate bricks or blocks. Another formula will be used for autoclaved, aerated concrete blocks. This is another type of concrete blocks. In this case, Fm prime is equal to Fuc prime directly. You don't need to find Fmv prime or you don't need to find Kh. Okay, so if we go quickly to the standard, I can show you this in the standard quickly here. So this is our standard for masonry under compression. So you can find all the explanation we have discussed here under this part. So this part in table 3.1 and table 3.2, because it is related to the probabilities of the member. So design probabilities. So here, if you have a look here, in this part, Fm prime equal to KHFMB prime for masonry of clay, concrete, calcium silicate units. Okay. For AAC, Fm equal to FUC prime. So this is under clause 3.3.2 can be found. Okay. So this is the compressive strength of masonry. Two formulas or two types based on if it is from concrete or clay or calcium silicate, or if it is from autoclaved aerated block. Okay. Another parameter, which is the grout. The grout is something that we need to use sometimes. Do you know what is grout means? You know, if you know what is grout means, or where we use in our no, grout is not the joint. The joint is the mortar. We fill if we want to uh, glue the bricks together. We glue them with the mortar. Grout, if we have a cavity wall, which means that we sometimes need to have two layers of walls, for example. So this one wall. And this is another wall. So we fill in between these two with what? With grout. So the grout is a filling material to fill the cavity between two leaves of the wall or the masonry. Okay, we call this one leaf or masonry leaf, and the other one is masonry leaf. This one use of the grout. Another use of the grout is to fill if we have a block. In some cases we have hollow block or blocks that have opening in it to reduce its weight. So if this is our block, so grout can be used to fill this core of the hollow blocks. So you can fill this part with grout. Okay, so this is grout. So these two options we may use the grout for. So what is the grout? The grout is a fluid concrete mix used to fill the cores of the hollow masonry units or the cavity between masonry leaves. So it is a type of concrete, but it is more flowable or more fluid. Usually the strength of the grout is around 20 MPa. So FC for the grout is 20 MPa with high slump to 30 millimeter slump to be more flowable. And the maximum aggregate size to be used is 10 millimeter maximum aggregate size. So this will make it more flowable, and the grout is limited by the strength of the masonry. So you can't use high strength grout because the brick or the masonry will fail before that. So it is limited by the strength of the masonry. Another thing is the design characteristic compressive strength of the grout, FCG, is taken as the lesser of two values. One of them is the 28 days cylinder the strength of the sorry cylinder strength or 12 MPa. Okay, so if you don't have test data, you cannot assume the mortar or the grout, sorry, less than 12 MPa. Okay, so this was some of the parameter we will need to have before going to the design methods. So now we need to know that we have two design methods for members under compression or masonry under compression. The first one is the design by simple rules covered in clause 7.3.3, and this method is simplified method and conservative method. This is the advantage and disadvantage of it. The other method is designed by refined calculation, which is in clause 7.3.4, and the advantage, it is not conservative or less conservative, but the drawback here in this time, it is complicated. Okay, so these are the two methods we will be looking at when we are designing the compressor, the masonry under compression. So before we go to the two methods, we need to find, or we need to know one of the properties of the masonry, which is FO, or the basic compressive capacity. So the basic compressive capacity, FO, has two cases. The first case is for ungrouted masonry. So if we don't have any grout in our masonry, so we can use the first one. If we have a grouted masonry, we have to use the second one. So for ungrouted masonry, FO equal to phi FM prime times AB. We will know the parameters now. For grouted masonry, we have two cases as well. If we have done tests for the grout, so we can use the second one. If we don't have any tests, so we use the first one. So for grouted masonry with no test done, FO equal to phi multiplied by FM prime AB. So it's the same parameter like before, plus additional value, which is KC times FCG prime over 1.3 multiplied by, sorry, to the power 0.55 plus 0.00 0.005 FCG prime. All of this multiplied by A gross. The other option, if test is done, so FO equal to phi FMG multiplied by AD. So we have three formulas, one of them for the ungrouted, two for the grouted, one for grouted with no test done, the second with test done. What are the parameters? Phi is the capacity reduction factor from table 4.1. So if we go to the standard here, if we go to section 4, this is table 4.1. So table 4.1 for the capacity reduction factors, we are looking at unreinforced masonry. So based on, we are designing compression today. If the block is solid or cored, hollow or grouted, so we can take the parameter phi. So phi for our case today, one of these three. So it can be 0.75, 0.5, or 0.6 based on the type of the block we are using. Fm prime is the characteristic compressive strength of the masonry. We have pointed to it earlier. AB is the bedded area of a masonry member cross section according to clause 4.5.4. We can see it here. So if you look to the plan view of the block, so this is the bedded area. The red is the bedded area, because if we have a racking means we have a setback in the joint. So if we have a setback in the joint, so we should subtract this setback from both sides. So the bedded area is the hatched red area in this case. This if we have a solid block. If we have a hollow block, so this area is a space or a core, so nothing here. So the bedded area will be only the hatched area here. Which is the face shell width. Okay, so this is the hollow unit case, and this is the solid case to find AB. AB will be clearer in during the example, but just a hint about what is AB. What is KC? KC is a factor here for grout. So Kc, a strength factor for grout in compression. Kc can be taken as 1.4 or 1.2. 1.4 for hollow concrete masonry unit of density greater than 2000 kilogram per cubic meter. So 1.4 only for hollow concrete blocks. 1.2 for all other masonry, which is clay, concrete, solid, and AAC and silicate. The next parameter is FCG prime, which is the design compressive strength of the grout based on or according to clause 3.5. AG is the design cross-sectional area of grout according to 4.5.7. FMG is the characteristic strength, compressive strength of the grouted masonry. So this is the strength of the masonry and grout together. AD is the design cross-sectional area of the member according to clause 4.5.6. So those are all the parameters needed to find the basic compressive strength FO. And here is an explanation of the cross-section dimension for AB or the bedding area. Okay, just one small hint here. It is racking. Racking means after you uh, like make the joint between the two blocks. So we have two blocks here. They use a tool to uh, create this rack here. Okay, this is just for maybe the final look of the wall, and also it help to fight some of the problems that face the the walls. So this sometimes needed to be done for our masonry walls. So the depth of the racking is the distance between the joint to the edge of the block. So this is the depth of the racking. So this part should be deducted from the bedding area. Okay. When to be deducted? If the depth of racking more than 3 millimeter. So if the depth of racking more than 3 millimeter, so you should deduct it. But if the depth of racking less than 3 millimeter, so no deduct. Okay, so this case 1 and case 2. Case 1 is here, case 2 is here. Okay, so this is for the cross-section dimension. So in summary, or just to give you some hints, AD, the design cross-section area, will be AD equal to AB in case of unreinforced masonry with no grout. For reinforced masonry, for reinforced or grouted masonry, AD will be equal to AC. This for reinforced masonry or grouted. Okay, we have two cases for the grouted. One of them is full grout. So the overall width times the length. This is area D or area C. So area D or area C equal to overall width of the wall multiplied by the length. Okay. For partially grouted, AD will be overall width of the wall minus the depth of racking if there is racking multiplied by the length of the grouted cores plus the bedded area of ungrouted cores. Okay, so if this our masonry wall, so this is our bedding area. So this is the length of the wall, and this is the width of the masonry. So AD in this case will be the width times the length. This for the full grouted. For partially grouted, it will be overall width multiplied by length of the grouted cores plus the bedded area of ungrouted cores. Okay, area grout. If you need area grout will be area D, area design minus area bedding. So this is the area of grout. So just a quick example here, if this our block, so as we mentioned, the bedding area will be the blue part. Okay, so area grout will be this part. So how to find area grout? It will be area design, the total area, minus area of the bedding, the blue area. So this is the blue, and area grout will be the yellow. Okay, so these are some of the dimension. Now we go to the formula for design for compression using the simplified rule or the simple rule, which is clause 7.3.3. So the design for simple rules, FD, the design or the factored compressive force and ultimate should be less than or equal to KFO. So this is the formula in clause 7.3.3. If we look to the standard here, so we are clause 7.3.3. So here is our formula here, 7.3.3.2. So the simple rules generally 7.3.3. The compressive on uniform symmetrical member, which our focus is FD equal to K times FO. So if we return back to our slide, FD is the factor design compressive force, which is the applied load in ultimate. FO is the basic compressive strength capacity we just explained earlier. Now what is K? K is the reduction factor for cylinderness and eccentricity, can be found using clause 7.3.3.3 or table 7.1. So K is an cylinder like reduction factor to account for cylinderness and eccentricity of the load. Okay, this means that K is a function of two things, which is SRS or SR and E. So these are the parameters that affect the reduction factor K. Okay, where SRS is the simplified cylinderness ratio. So SRS will be used for the simplified method. Okay, so here is the table to find reduction factor K that account for cylinderness and eccentricity for simple rules. So to use this table, 7.1, we need SRS, the simplified. So if we know SRS here, according to the number and according to the eccentricity of the load. So if we have concrete slab at top, concrete slab at bottom, or floor or roof type other than concrete slab, or like more stories. So we have three cases. So you can select the factor K. So the factor K will be one of these values here. So to enter the table, you need one, the SRS value. Number two, you need to know the slab type. Slab type to know what the eccentricity is. Okay. So the first thing is we need to know how to get SRS. So SRS or the simplified cylinderness ratio. SRS can be found using the formula AV times H divided by KT times T in clause 7.3.3.4. So SRS equal to AV times H divided by KT times T. So this is our formula where AV is the vertical cylinderness coefficient equal to 1 if the member is laterally supported along its top edge and equal to 2.5 if the member is not laterally supported along its top edge. So AV can be two values, one of two values, 1 or 2.5. 1 if it is laterally supported, 2 is unsupported or laterally unsupported. Okay, so this is the value of AV. H is the clear height of the member between the horizontal lateral support in millimeter. So H is the clear height of the masonry wall. Okay. KT is a thickness coefficient come from table 7.2. So if we have a look on table 7.2, here is table 7.2. According to the uh, the the wall, the wall contain or include beers or not. So table 7.2 for the thickness coefficient KT for walls stiffened by monolithically engaged beers. So if we look to here, this example here, So in some cases, we add some beers to stiffen or to support laterally support the wall. Okay, so this is stiffen. If no stiffened or no beers, so you can take KT as 1. So KT equal to 1 if there is no engaged beer. But if you have beer, you should consider table 7.2. So how to use 7.2? You need to know the bearing spacing divided by the beer width, where beer spacing is taken as the distance between center line of the beers. Another thing is you need to know the beer thickness ratio, which is TWB to T, where TWB is the overall thickness of the masonry wall, including the engaged beer. T is the overall thickness of the masonry unit. So if we go back to the drawing, T wall is this T, the original or the thickness of the wall without the beer. TWB or the beer, the width of the wall including the beer, TWB. So you can find TWB divided by T. Okay, so you can find this value, and for the beer spacing or beer to the beer width, you need to know what is the distance between this beer, if this is our center line. So if we consider this the center line of the beer, so from here to here is the beer spacing. If we consider that we have another beer somewhere here. Okay, so if you know this data or this information, you will be able to find KT. If you know KT, so you can find SRS. Where, again, what's T? T is the overall thickness of the member cross section perpendicular to the principal axis under consideration in millimeter. So T is the thickness of the wall we got here, or masonry member thickness. The overall thickness of the member cross section perpendicular to the principal axis under consideration. So if we know all the parameter AV, H, KT, T, we can find SRS. If we know SRS, you can go to table 7.1 to find the value of K. If you know K, so you can find the value KF note and compare to the design or the design, yes, the design compressive force. Okay. Do you have any question, guys, about that? No? Okay. Do you want to have a rest for 10 minutes? Okay. So just add it here. So we can have 10-minute break and we can meet again at 2:10. Okay, I will see you in 10 minutes. Thank you. Okay, guys, can we continue now? Okay, so just to delete this page. So let's have a look on Thanksgiving and Shanghai. So let's have a look on our first example today. Our example today. So example one, we need to design a wall 4 meter long and 2.7 high, carrying a concrete slab with a total factored load on the wall of 50 kN per meter. Support to the wall is provided by intersecting wall at the side and the slabs above and below. The material is 90 mm thick clay masonry with M3 mortar 1:1:6, and brick strength FUC is 20 MPa, given that FM is 6.3. So in this example, the dimension of the wall is given, the load or the factor load on the wall is given, the lateral support by other wall and the slab is given or known for us. The block is 90 mm thick clay, type of the masonry is clay. The mortar type is also given, M3, and also the percentage of the water and sand and cement ratio are given. The strength of the brick is FUC prime is given as 20 MPa. If M prime for the masonry is 6.3 MPa. So let's have a look on how to start. The first thing is the bedded area. So here, as you know, we know to find the basic compressive strength of the wall, FO. So FO equal to phi FM prime times AB. Where does this come from? If we go up, so we don't have any information about grout or no grout, so we use ungrouted compressive strength, phi FM prime AB. So this is the start. So we need to know the parameters in this formula. So the first parameter is AB, or the bedded area, which is 90,000, because the brick width is 90 mm. So we will calculate for 1 meter of the wall only. So 1 meter means 1,000 millimeter. So this means the bedded area is 90,000. So this also means that no information was given about what? No racking. So no information about racking, so we consider no racking. So AB will be the width time 1000. So the basic compressive strength be FO according to AS3700 formula 7.3.21. This is our formula, phi FM prime AB. The capacity reduction factor phi is 0.75 if we want to check that. So if we go to table 4.1, you need to get to be familiar with the standard so that in the test you can easily find the parameters. So here we are designing unreinforced masonry under compression, solid or cooled. So phi is 0.75. So this means FO equal to 0.75 times the given FM prime. Given F prime is 6.3 times AB. So AB equal to 90,000 millimeter square. So FO equal to 425,000. Okay. If we want to get it per meter, so FO will be 425 kilonewton for each for sorry for each 1 meter of the wall, for each meter of the wall. Okay, this is how it is written. Okay, so this is FO. Now what is the next step? We need to design according to the simplified method. So before we go to this step, the simplified method or the simple rule method, sorry, both of them are okay, but let's call it as it is in the standard. So the simple rules method mentioned that FD should be less than or equal to KFO. So we know KFO, so we still need to find K. To find K, we need to go to table 7.1. To go to 7.1, we need two things. The first thing is SRS, or the slenderness ratio based on height. So SRS equal to AV times H divided by KT times T. As there is no engaged beers, so KT should be 1. The vertical slenderness coefficient AV equal to 1. How AV equal to 1? If we go back to AV, what is AV here? EV is 1 if the member is laterally supported along its top edge. Here in this example, what we have at the top edge, the support is provided by the slab above and below. This means that our wall is supported on the top by the concrete slab. So the top end here is laterally supported from the given information, which mean AV equal to 1. H is the clear height, so it is 2700 given to us. T is the thickness of the wall given to us as 90. So 2700 is the clear height of the wall. 90 is the wall thickness. So this means that SRS is 30. Okay, so what is the next step? You should go to table 7.1 to find K. So if we open table 7.1, where is table 7.1? Here is table 0.71. So we know that SRS 30. So it will be one of the values from here. So which one of them to use? According to our case, which case of the three? We have slab at the top, slab at the bottom. So we are in this column. So our parameter K will be equal to 0.35. So this means that FD, sorry, the formula is FD less than KFO. So we know that FD equal to, from the previous step, 425 kilonewton for each meter. The other side, 0.35 times FO. How much is FO? Sorry, this FO, not FD. FO is 425. FD is 50. So this is our FD equal to 50 kilonewton per meter. So here also, I will replace this text here with what? 0.425 divided by meter. Okay, so if we go to our formula, FD is 50 kilonewton per meter, should be compared to 0.35 times 425, which is equal to 149 kilonewton per meter. So this means that FD is less than phi or KFO. So this means our design is okay and safe. So the design is safe for this wall. Okay, is that clear? Do you have any query about this example? Okay, so this was the simple calculation. Now we need to find, or we need to go through the refined calculation. So the refined calculation according to clause 7.3.4. So in the refined calculation, same formula for the design. FD should be less than or equal to K times FO. But now the idea is how to find K. So K will be calculated or determined using the refined calculation. So SR, so K will depend on what? SR, not SRS. So SR is the slenderness ratio, not simplified, according to clause 7.3.4.3. So if we go to the standard quickly to see this part in the standard section 7. So this was the simple rule, and this is the simplified slenderness ratio. 7.34 design by refined calculation. So same formula, FD less than KFO, but the idea is how to find K. A reduction factor for slenderness and eccentricity using clause 7.3.4.5. Okay. So K will be the reduction factor according to 7.3.4.5. And now if we return back to our calculation, so we need to find SR and K using the refined calculation. SR slenderness ratio according to 7343. K is a function of SR, E1 over TW, and E2 over E1, and the Masonry type, where E1 and E2 are the load eccentricities at top and bottom end of the wall. Okay, for K, it will be the lesser of two cases. One case is the lateral instability case, and second case is the local crushing case. So if we go to the standard to see, so K, according to this clause here, for refined calculation, we have two cases. One of them is lateral instability and local crushing. So we will find the two values and then select the lesser of both. So this is the first one, and here is the second one. Can be any of this. Okay, so these are the idea for the refined calculation, and let's see how to go through that. So for close 7.43 SR, we have cases. For case A, for a wall that is laterally supported along one or both of its vertical edges and subjected to design compressive force, which is FD less than 0.2 FO. So SR will be the lesser of two values. So in this case, we have two values and we will select the lesser. So what this mean? We have a wall that it is supported along its one or both vertical edges. So these are vertical edge for the wall, vertical edge of the wall. So if it is supported on one or two vertical edges, so SR will be the lesser of these two, similar to before. This is similar to the simple rule, or this one, 0.7 over T, AV, H, AH divided by, multiplied by L under the root. So we know AV, we know H, we know KT, we know T from before. So we still need AH and L. L is the width of the wall, length of the wall. What is AH? So here is AH and AV. Here AV is the vertical slenderness coefficient. It has different value compared to before. Before it has only two values. Now it has 1, 2, 3, 4, 5 values. So it can be 0.75, 0.85, 1, 1.5, 2.5. 0.75 for wall laterally supported and partially rotationally restrained at both top and bottom. So it is like the edge conditions of the top and bottom end. So AV, consider the edge condition for top and bottom ends of the wall. So based on the given information, you can decide if it is 0.75 or 0.85 or 1, 1.5 and 2.5. Okay, so this for the factor AV. So the factor AV here is a little bit more details compared to the previous case. AH is another factor we need to know, which is the horizontal slenderness coefficient AH. So this is considering the edge condition of the side of the wall, or the vertical sides of the wall. The two vertical ends of wall. So if this is our case, so it will be considering these two edges. For AV, it is considering top and bottom edge. So top and bottom. Here it's considering, in other words, the left and right edges. So also we have two cases here. AH can be 1 for walls laterally supported along both vertical edges, or 2.5 if the wall laterally supported along one vertical edge and unsupported along its other vertical edge. So 1 if it is supported along both edges, 2.5 it is supported only in one edge. So here is case A for walls that it is laterally supported along one or both edges. The other case B, when we have opening in the wall are such that the masonry between any two consecutive openings is by definition an isolated pair, the slenderness ratio of that isolated pair shall be taken as SR, in this case equal to 2H1 divided by T, where H1 is the taller opening height. Okay, so we are considering this case, if we have openings, so we are considering the part of the wall between the openings. All other cases will be case C. So if you have wall that is not supported by any of each edges, so SR will be the original formula or the basic formula, AV multiplied by H divided by KT times T. So this is our general formula. So according to the given data in the problem, you will be able to find the factor SR in these three cases, and here is AV and here is AH. For the eccentricity E, the wall eccentricity, we need to find A1, E1 and E2. Okay, so E1 and E2, E1 is the larger eccentricity of the vertical force at either top or bottom of the member and not less than 0.05 TW. E2 is the smaller eccentricity of the vertical force at the other end of the member, not more than E1, and negative when the eccentricities are in opposite sides of the member, i.e. reverse curvature. What does this mean? That E1 is the largest eccentricity. E2 is the smallest or the smaller eccentricity, because we can have eccentricity from top, eccentricity from bottom. So let's start to find what is the eccentricity. So the eccentricity, if you have slab resting on a wall like this, so actually the load from above, which is the load from a different wall, for example. So is W1. This is the load from above. And the slab load is W2. So load from slab, W2. Load from above or other walls is W1. So here, actually, we need to find like a combined eccentricity. So E equal to W2, because it is a triangle. So the centroid of this triangle is at 1/6 of the thickness of the wall, so TW over 6. So this means the eccentricity from top here, for example, eccentricity from top equal to W2 multiplied by TW over 6 divided by W1 plus W2. So this is the equivalent or combined eccentricity E1. Okay, so we have W2 multiplied by this distance and W1 already passing through here. So the eccentricity will be W2 multiplied by T1 over 6 divided by summation of W. And this is the general or the most common case we have. So you have a slab resting on a wall. So the slab load is not acting at the middle of the wall. It actually acted as a triangle, like the stress is triangle, so it's acted at TW over 6 from the center. So this first case. Second case, if you have eccentricity for cavity wall. So for cavity wall, we have two leaves of the wall. And we have like grout between the two leaves. So here the load from slab will be acted at, if we said this T wall over 2, so it will be acted at T wall over 2 divided by 6. Okay, same case, but the difference is T here is half T here, for example. Okay, the third case, if we have load from top W1 and 2 load from slab left and slab right. And slab left and slab right are different, so W2 and W3. So you have E, the total eccentricity, will be W3 plus W2 multiplied by TW over 3 divided by summation of the three loads. So E equivalent here will be W3 plus W2 multiplied by TW over 3 divided by W1 plus W2 plus W3. Because we have eccentricity from left, eccentricity from right. So the eccentricity will be, I think this should be minus, because this one of the forces rotating in clockwise, the other one rotating anti-clockwise. So actually the eccentricity will be the difference between both. So this is another case if you have slab slab from both sides. But W2 doesn't equal to W3. If I ask you one special case, if W2 equal to W3, how much is E? What do you think? If W2 equal to W3, E equal to how much? Do you have any idea? Nothing? It will be 0. So if the load from the left equal to the load from the right, this means the two moments will eliminate each other, so it will be 0. Okay? So this is how to find the eccentricity of the load. If we know the eccentricity of the load, so we can find the reduction factor K according to clause 7.3.4.5. So we have two cases. We will calculate for both cases and K will be the lesser of these two. So for lateral instability, K equal to 0.5, E2 over E1, 1 multiplied by 1 minus 2.083, E1 over TW. So E1 and E2 load eccentricity. TW is the wall thickness. SR is the slenderness ratio. So we know all the parameter, so we can find K. For local crushing, for member of solid cross section, so if it is solid, so K equal to 1 minus 2 E1 divided by TW. For members with face shell bedding, or in other words, it is hollow. So K equal to 1 minus TFS divided by TW divided by 1 minus TFS over TW plus 2 E1 over TW. So we know TW is the wall thickness again. TFS is the face shell bedding thickness. So if you have a brick, we mentioned that we have hole. So this is the face shelling thickness. So this is our TFS. Okay, so you have to calculate two cases for K, and then we will select the lesser of two cases, this considering the two failure mode of it. Okay, where the E1 and E2 is the larger and smaller eccentricity. TW is the wall thickness of the wall, overall thickness of the wall. TFS is the thickness of the face shell for hollow block masonry, or the flange thickness for diaphragm walls. And now we have another example for walls under compression. So in this case, we have, or in this example, we have cavity wall, 5 meter long and 2.7 meter high, supported on one side or one vertical edge with a window at the other edge. So we have window from side and support from another side. The wall is at the ground floor level of an apartment building with a tiled roof and supports two higher floors having concrete slabs, which span 6 meters onto the inner leaf of the cavity wall and are subjected to floor life load of 2 kPa. The factored load on the top of the ground floor wall is 170 kilonewton per meter, comprising 100 from above and 70 from the first floor slab. The ground floor slab is on fill and isolated from the wall. The material is clay masonry with M3 mortar and brick strength of 20 MPa. Use standard brick size 230, 100, 670. So this is the brick size. Okay, so let's have a look and interpret the given information. So here is the wall we are looking at. So it is cavity wall, means we have two leaves. The height of the wall is 700. The wall is ground floor wall, and the building has roof and two slabs. The load from top is 100 kilonewton per meter, and from the first floor slab is 70 kilonewton per meter. So that means we have eccentricity. Okay, so this is a drawing for this example, but we still have live load. So this from here the dead load, the dead load, the factored load on the top of this. This is the factored load. So this is the factored load part. Okay, so let's start calculation. So Fm in this case will be 6.3 MPa, not directly given, but if we look to table 3.1 here, so according to table 3.1, we can find the factor Fm prime and Fmb. So what is the type of masonry? Clay. The bedding, let's have a look again. The type of the material is clay, M3 mortar. So clay and M3 mortar. So M3 and clay. And what is FUC? FUC given as 20 MPa. So we have 20 MPa and clay M3. Okay, so let's have a look if there is any other information given. So the material is clay masonry with M3 mortar and the brick strength FUC 20 MPa, and the brick size is 230, 110, 76 millimeter. So if we go back to our table, so we have clay, bedding is full, M3, 20 is FUC, so FMB prime is 6.3, and we know from before that Fm equal to Kh times Fmb prime. So the first thing is Fmb prime 6.3 from table 3.1. Now Fm prime equal to Kh times Fmb. B. How much KH for this type? KH come from table 3.2. So from 3.2, KH is 1. So ratio of masonry unit brick to the mortar bed joint thickness. So KH, based on this calculation, it is taken as 1. So this means that we assume that the ratio of masonry unit height to mortar is 7.6. So this give us KH equal to 1. Okay? Is this okay with you? So we assume KH as 1 in this case based on the calculation given to us. So now we need to find FO again. So FO equal to phi FM prime times AB. So we need to find the bedded area. So the bedded area, we have a brick. The brick width is 110 millimeter. So the bedded area will be the width multiplied by 1 meter, which is 1000 millimeter. So it is 110 times 1000 equal to 110,000 millimeter squared. So again, ungrouted masonry. So FO equal to phi FM prime AB, where phi is 0.75 for ungrouted solid under compression. So this means that FO equal to 0.75 times 6.3 times 110 millimeter. So this means that FO equal to 520 kilonewton per meter. So similar to before, we got FO 520 kilonewton per meter. Here we can use the simplified method as well for comparison. So this example, we are calculating both to compare. For the simplified method or the simple rule method, the slenderness ratio, SRS, equal to AVH divided by KT times T. Okay, so no engaged bears, so KT equal to 1, similar to before. Vertical slenderness coefficient, AV equal to 1 because it is supported at top edge by the slab. So this means that SRS equal to 24.5. So we can go to table 7.1 or clause 7.33a to find K. So if we go to the standard quickly, 7.1, so you can find K using these formulas. or from table 7.1. So for table 7.1, we don't have SRS 24.5, so you can use interpolation. Okay? And here, if we just round it down to 424, so SRS. So which parameters to use can be this one or this one or this one. So our slab case is this one. We have like multiple story and we have load from the slab. So it will be around 0.047. So it will be around 0.047. This is a factor K. Uh, mm. Should I just have a look on this one again? Hmm. Here, close 7.3.3. So if you go up, which case is this one? For wall with load applied to the face. Ah, for wall be supporting. Okay, so this not the case. Just this only of the load is hanging outside of the load. Sorry. So this is not the case we are looking at. Okay. Here only if the load, if we have a load like outside of the wall. This is not our case, so we are using same case again here. So the factor will be around 0.47. Okay. So this is the factor we should use. It is approximately 0.47 or 0.46. So this means that FD equal to 170 kilonewton per meter compared to 0.46 or 0.47 times FO. How much is FO? 520 here. So 520 kilonewton per meter. So this is KFO. So now FD less than or equal to KFO because KFO in this case equal to 239 kilonewton per meter. So this means the design is safe. So this wall under compression is safe. So this was using the simple rule. For the defined calculations, okay, for the defined calculation, SR equal to AV times H over KT times T. Okay, why we use this one? If we go to the earlier slides, how can we find SR? So SR for wall that laterally supported along one or both if its vertical edges and subject to design compressive force FD less than zero point 0.2 F. Or where opening in the wall are such that the masonry between any two consecutive opening is by definition an isolated pier, or SR for other cases. So actually in this example we will use this one because this is the case that we that represent us, because our wall is not supported or not laterally supported by any of its vertical edges, so we can't use A. So which one we will be using? Case C. Okay. So because the information given to us didn't mention anything about the but actually it is supported at one edge. Okay, sorry, I just here. Let's leave this one now. So actually, if we look to this example here, so for the refined edge, we need to find SR first, sorry, SR using case A because our wall is supported at one of its vertical edges. So if it is supported at one of its vertical edges, so we can use A. Okay, but here we don't have the panel action because FD is more than 0.2 FO. So if we check that FD, how much is FD? 170 kilonewton per meter, more than 0.2 of 520. 0.2 times 520 is 104 kilonewton per meter. So this means that we will be only using this formula, and that's it for the SR. Okay, so you need to calculate SR using this form, not the other two. Okay, I will stop here because we already exceed the time, and we will continue next week. Okay, do you have any question, guys? No? Okay, thank you for attending today. Thank you, Brendan. Thank you, everyone. We'll see you next week. Thank you, Yifang. Bye, Yifang. Thank you. See ya.